everyone. Welcome back to another video. In this video, we will be discussing about the lesson energetics. So I think from the name itself, you would know kind of what are we going to discuss. Yes, we're going to discuss about terms related to energy, and we'll add some bit of the chemical, uh, bit of the chemistry into it, and then we'll see what it is about. All right. So by the end of the video, you'll be able to recognize what are exothermic and endothermic reactions. Then, in order to represent them, we use something called energy profile diagrams. So you would know how to represent them in energy profile diagrams. And finally, we will learn about how do we determine the enthalpy of a reaction, of a chemical reaction. There are two ways to do it. So we'll discuss both ways that are possible to determine. All right, let's move forward. All right, yeah. The first part now, this is, we go in this lesson called energetics, and the so energetics, we said, it's the term used for energy. But when it comes to chemistry, we just change the term energy. We just advance the term energy a bit, and we call it as enthalpy change. Okay, so the energy change we refer in chemistry as to be the enthalpy change. So basically, enthalpy change is none other than the amount of energy that is being absorbed or released during a chemical reaction. All right, and be mindful that to see that the delta, the enthalpy change is represented by delta H. This triangle out here is delta. Delta means it's a Greek letter from the Greek alphabet. Delta means always when we want to represent uh, change. Again, we want to represent change in scientific notation. We use the uh, symbol delta. All right, and H represents the enthalpy. Okay, so this is called change in enthalpy, and or you can say in easy words, enthalpy change. Again, refer it as delta H. So because no matter what wording we give it as enthalpy change or energy change, both are same. So therefore, we are able to measure them in terms of kilojoules, but because we are here interested in the form of chemistry in it, we always will be looking at the energy released or absorbed per mole. All right, so per mole, how much of energy is being absorbed or released by or during a chemical reaction is the thing that we are gonna talk about in this enthalpy lesson. All right, so now we spoke about that there are two types. Okay, so there are reactions that could be energy which is being released to the during the reaction, or during a reaction energies can be absorbed. So based on that, we are able to classify two types of reactions, which are endothermic and exothermic reactions. So both of them have their own characteristics, and we will look into what they are. All right. So first in case we have is the endothermic reaction. So endothermic reaction, what is endothermic? So basically, when two substances react, okay, so say you have two reactants and they react, and during the reaction, the reactants are able to absorb energy or absorb heat from the outer surrounding. So normally, if you are, if you want to make use of our sensors, the best way we can observe whether energy has been absorbed or released is by measuring the heat of it. So for example, when an endothermic reaction happens, initially the vessel would be at a warmer temperature, but as the reaction goes on, the vessel will get cooler because all the energy that is around the vessel is being absorbed by the reaction. All right, or by the, we could say, by the reactants. Okay, So that means the compared to the reactants, the products will have a higher amount of energy because initially they have some amount of energy, and by the end of the reaction, it has absorbed energy from the surrounding, and then that means the products need to have a, a great amount of energy. All right. Now this information, this enthalpy change, okay, or this endothermic reaction can be represented in a particular diagram, like a graph, which we refer it as energy profile diagram. Okay, so this is the energy profile diagram. As you can see, the y-axis, we are only worried about the y-axis because the y-axis tells us the energy. So you can see in this, for this is the energy profile diagram for the endothermic reaction. So we can see that the reactants are at a lower energy in comparison with the products, which are at a higher. And you can see that the change in enthalpy is a positive value, because always what we see is when we calculate enthalpy, it's actually the energy, the final energy minus the initial energy. Okay, so here you can clearly see that the final energy is greater than the initial energy. So that means the energy change or the enthalpy change should be a positive value. All right. So normally we cannot categorize each and every kind of reaction to say, okay, this particular reaction is endothermic, this particular reaction is exothermic. But there are certain cases that we can classify. So decomposition reactions, okay, decomposition reactions are an example for endothermic reactions. So if you want to decompose calcium carbonate, magnesium carbonate, or nitrate, or anything like that, all of them uh, uh, will be absorbing energy from the surrounding and acting as endothermic reactions. All right. So moving to the next one, we'll look into the exothermic reaction. So exothermic reaction is the complete opposite of it. So during exothermic reaction, what happens is there are two reactants. There are reactants. They will react, and during the reaction, energy will be given out to the surrounding. Okay, so that means whatever energy that is there initially within the reactants, by the end of the reaction, that energy will be gone down. Okay, so for example, that means the reactants will have high energy, but the products will have lower energy. So that also we can represent in this energy profile diagram. This energy profile diagram, so you can see the reactants are at a higher, having a higher amount of energy when in comparison to the products. So you can see the arrow that we have seen. This arrow is pointing downwards. Okay, so here also you can see that the delta H, the enthalpy change, is a negative in this case. Why? Because we said that the enthalpy change is measured as for the final enthalpy minus the initial enthalpy. So here the final enthalpy is much lower than the initial enthalpy. So if you do your arithmetic, you could infinitely validate that the enthalpy change should be a negative value. Okay, so reactions such as combustion, neutralization, displacement, all right, and reactions of metals with acids are all examples of exothermic reactions. So combustion reactions, you guys know that when you combust something with oxygen, so those reactions, the neutralization reactions, are reactions with between acids and alkalis, and then displacement reactions, there are so many with regard to different metals and stuff like that, and also reactions with metals with acids. So metals with acid means you can have you know magnesium plus sulfuric acid or something like that, and all those will be exothermic reactions. So the observation, if you do this, if you do a particular exothermic reaction practical in the laboratory, what you would see is, so initially the vessel would have a certain amount of temperature, and as the reaction goes on, the vessel heats up. Okay, so that's one way you can say, okay, the heat that is, or the energy that is stored within the that is there within the reactants, by the end of the reaction they all give it away, they give it to surround. All right, so that is one you know, observation that you can do with your senses. All right. Now we move on. Now, you know, not in all cases, okay, not in all chemical reactions we can, rely on our senses so much, okay. So therefore we need to, come up with a, very practical way and a very, more reliable way of getting this enthalpy change. Okay, so there are basically two ways of getting this. One way is the practical way, which I would discuss in a few moments, and the other way will be the theoretical way, where you would be given some values and then you have to calculate something like that, perform the small arithmetic, and you can arrive to the answer. But first of all, let's look at the practical way. Okay, so here what you do is, okay, so here you need to perform a small practical. This practical, but there's not a much, there's not a big amount of equipment that you need. You just need a beaker, then you need a you need a insulating cup. Okay, why do we need an insulating cup? Because we don't want any heat to, go out from this thing. We just want, everything to be, we don't want the outside factors to affect our enthalpy change. All right, we want to make this experiment as fair as possible. All right. So we definitely need a thermometer because we're going to see the temperature change, and then we need our particular any kind of the reactants we want. So in this case, in this example, we are using HCl and NaOH as our reactants. So so what we do here is right now we put the NaOH and the HCl, we put there and we let them react. So before putting them into the particular beaker, what we do is we first of all measure the initial temperature and we record it. So without any reaction, the temperature would be the initial temperature. But after we put both of our reactants and we make the reaction to, react, and after some time we are gonna uh, look at the temperature. So if it's exothermic temperature, you would see the temperature rising very quickly. If it's endothermic reaction, you would see the temperature going down from the initial temperature. So in this case, we are doing a neutralization reaction. So definitely a neutralization reaction is a exothermic reaction. So you would see the temperature going up rapidly. So uh, the final temperature that we record, should be the maximum temperature. Okay, because what happens in this reaction is the reactants will react, they keep on reacting, they keep on reacting, and they come to a point where they stop reacting. No more reaction happens. And at the point where they stop reacting, that will be the maximum temperature. Because beyond that, what will happen is the temperature will slowly, gradually move down again. So we need to be cautious and we need to record the maximum temperature. Okay, so maximum temperature is the final temperature. Okay, so then are we done with what we have? No, because our aim in doing here is we want to find the energy, right? We want to find the energy. So for example, now what we have done is we've just, found the temperature change. So how are we going to relate this temperature change into the energy that we want? All right, so what we do is we use this equation, E equals mc delta theta. Okay, so here E is the energy, m is the mass in grams. Okay, C is the specific heat capacity of water. I think in physics you might have learned this. So and this entire formula you must have learned it in physics. It's very useful formula in physics. And then we have here delta T. So delta, as I said earlier, delta means change, and T is the temperature. Okay. So We do all this, we plug in the numbers, we plug in all the numbers that we want, okay, and then we are able to find the energy what we want. But the problem here, we come to a problem, okay. The problem that we come here is, now this particular kilojoules, okay, this particular joules or kilojoules or whatever energy that we get is for the amount of uh, moles that are reacted within this two reactants. But what does enthalpy change say? Or the enthalpy, what does it say? Enthalpy should be kilojoules per mole. So whatever moles we have in this case, so what you should do is, you should first of all find the number of moles, okay. So first of all, you know, you found your energy, now you're finding the number of moles. So then you're going to use the ratio method and say, okay, this amount of joules, I for this amount of moles produces this amount of joules. So for 1 mole, how many joules are being produced? Now this particular X value that is here, that will give you the enthalpy change. Okay, so be very mindful that we are always associating with enthalpy change is kilojoule per mole. Okay, for every mole, how many kilojoules are changing? That's what we want to know. Okay, we don't want to know for 0.25 or for 0.5 moles how much of energy enthalpy change is there. Okay, so after performing that, you would see um, that you are getting this particular value 10%. So this is according to my calculation that I have done for the example that I've done here. So you get 10.00, 10.04. Okay. So, and then remember that then now here you will get a positive value, but we know according to our the theory, we know if the energy is being given out to the surrounding, or if the final temperature is greater than the initial temperature, that means it is an exothermic reaction. Exothermic reactions, what do they have? Their enthalpy change is negative. So always remember to put a negative sign if it's a exothermic reaction, because all values that you get until now, you will get all positive values, but be mindful to add that minus to indicate that it is an exothermic reaction. If you just put 10.04 and you just say exothermic reaction, then it is not exothermic reaction, because exothermic reaction enthalpy changes are negative. All right, so a few things to be mindful of, and yeah, let's move on. Okay. Next one is, if you determine enthalpy change, say you don't want to, fuss yourself too much and go to the laboratory, prepare all those solutions, be mindful of the temperatures. You don't want to do anything. You just want to take the shortcut of it. And do we have a shortcut? Of course we do. Of course we do. Because many chemists in the world, many scientists, many chemists, they have already done these experiments. They've found certain energies, they found bond energies, and they've recorded into your books, and you all have all those facilities available in the textbooks and even in the internet. Okay, so here what we want is, we are going to use the bond energies to determine the enthalpy change. Now, if you look at here, there are a few things that you have to be mindful here. As chemistry students, we know during a chemical reaction, certain bonds are broken, certain bonds are formed. Okay, if something is broken, something's formed. That's like Newton's law. Okay, if something happens, if action is performed, a reaction is done, is committed automatically. Similar here. Okay. So bond breaking. So if you want to break a bond, what should you do? If you want to break a bond, you should give a energy, right? You should give force. So based on the two types of reactions we know, endothermic and exothermic, is definitely endothermic reactions that supply energy, to break bonds. Because exothermic does not supply energy, exothermic gives away his energy. So he can be the reaction that breaks bonds. So endothermic reactions uh, I is require the is the is a reaction which is involved in bond breaking. And similarly, exothermic will be associated with the bond making. All right, be mindful of that. Yes, use your common sense a bit. Okay. Now, delta, the delta H or the enthalpy change, we have a small formula. You can just memorize this formula. So delta, the enthalpy change is basically bond breaking minus bond making. All right. So in other words, you can just say, you know what, bond breaking is endothermic, bond making is exothermic. So you can just say endothermic minus exothermic also. So remember it in any way you want. Okay, no problem. Okay, so I have a example there. We are reacting this CH4. You learn this in the when you go to grade when you do organic chemistry. You will learn that this is a methane molecule. Okay, this methane, it's organic molecule. So we are combusting. We are combusting this methane with oxygen, and we get carbon dioxide and water. So what are we doing here? So look at here. These reactors. These are the reactors. This is the product. This is not a reversible reaction. It's just a irreversible reaction, one-way reaction. Okay. So that means on my left side I have my reactor. On the right hand side I have my products. So these guys, the CH4 and the oxygen, those bonds need to be broken. The bonds between, now here I have drawn displayed formulas to show you the bonds that have been broken. So look at here. Now the CH4 has 4 CH bonds. It has 4 CH bonds. So all of these CH bonds should be broken. Similarly for oxygen, if you can see, oxygen has a double bond. Here, oxygen has a double bond. So this also should break. So these left hand side will be the portion where the bonds are being broken. That means the endothermic reaction happens on the left hand side. Whereas in the right hand side, the bond making happens. The new bond, the carbon dioxide is being formed. The water is being formed. So there is a bond making. All right. So that is the first principle you need to know. And these values, CH, these are the bond energies. These energies will be given to you. These are recorded in textbooks, on the internet, as I told, it's everywhere. Okay, where if you want to find, you can find. No restriction. No one's gonna tell you anything. So these values are there. What you need to do is perform the arithmetic, calculate the bond breaking, calculate the bond making. All right, and then you do your arithmetic. So look at, you can see, so bond breaking, 4 CH bonds are broken. So one CH bond has 413 kilojoules per mole, but we have here 4, so we multiply that by 4. Oxygen has a 498, but here we have 2 of them, so you multiply by 2. So all of that you add. So 2648 kilojoules per mole is the bond breaking. That is the energy associated with the bond breaking. Then if you go to the bond making side, you have carbon dioxide, carbon and oxygen. Okay. So carbon oxygen, one of these bonds is 743, but we have 2 of them, so we multiply by 2. And then we have the OH bond, which is 464, but here we have 4 of them, so you multiply by again by 4. And you perform your arithmetic and you arrive at an answer of 3342 kilojoules per mole. So that is the amount of energy used in bond making. Then what do? You simply plug in both these values, 2648 and 3342, into this particular equation. And you can, if you plug into these equations, you can see on the right, you get a value of a enthalpy change of minus 694 kilojoules per mole. All right. So you can see here straight away, if you perform the arithmetic, you would arrive at a negative answer. So negative enthalpy means it's a exothermic reaction. If this answer was a positive, then we know it's an endothermic reaction. There's nothing to think about. You just perform the arithmetic and get the answer. Unlike what we did for the determine the enthalpy using the practical method, where you have to keep certain things in mind. Okay, so this is it for this enthalpy lesson. Okay, this energetics lesson. So what we discussed was we discussed about exothermic and endothermic reactions. We said exothermic reactions are reactions where the energy is being given out to the surrounding. Endothermic reactions are the energy is being taken from the surroundings, right? And then we discussed the energy profile diagrams. Those are the graphs that we represent these, that we are able to represent these two reactions. All right. Remember how to represent them, and remember that the delta H or the enthalpy change associated with exothermic reactions are always negative, and the enthalpy change associated with the endothermic reactions are always positive. All right. And then we discussed about determining the enthalpy change using the practical method. So remember the practical, remember the apparatus that is used, and then be very mindful about the, you came across a new formula, E equals mc delta t. Okay, so remember how to obtain the kilojoule per mole, and remember to indicate whether it's exothermic or endothermic reaction. And then finally we came with the enthalpy change with associating with the uh, using bond energies. So here also we understood that bond breaking is endothermic and bond making is exothermic. So keeping that in mind, we do the small arithmetic that we had to do, and then we apply to this formula, which we know, which we learned today, is enthalpy change is equal to bond breaking minus bond making. We plug in the values to that formula, and we obtain the value, and based on the sign, if it's a negative sign, it's exothermic reaction. If it's a positive sign, it's a endothermic reaction. All right, so that's it for today. So hope you understood what we discussed today in the class. Thank you, and have a nice day.